So, we know how to graph linear and quadratic functions, but what about exponential growth functions? Unlike linear functions, exponential growth functions increase at an increasing rate, which leads to large amounts a lot quicker than linear functions. An example of this would be bacteria cultures or population growth, which increase faster the more there are. So what makes an exponential function? Well, they're similar to quadratic functions in the sense that they both use exponents. However, this time it's the exponent that has a variable rather than the base. So for example, the quadratic function we're used to is f at x equals x squared, but now it would be g at x equals 2 to the power of x. Let's see a visual. A bacteria culture doubles every 6 hours. If the culture starts off with 3 bacteria initially, how many bacteria will there be after A, 2 hours, and B, 3 days? To solve this, you could multiply the original amount by a certain number of 2's to find the number of bacteria at each 6-hour interval, but this gets pretty hard once the larger numbers start to come up, and it poses the problem of getting a certain amount of hours that isn't a multiple of 6. Luckily, there's a formula to help us out. In general, the equation that expresses exponential growth is p equals p naught times r to the exponent of k times t, where p is the final amount, p naught is the initial amount, r is the rate of growth, k is the growth constant, and t is the amount of time. We'll start by writing out the equation. P equals, we're solving for p, which is the end population, and then we find that there's 3 bacteria to start, so that's p naught, the initial population. Then we go to find the rate, which is double, so it's 2. If it would be triple, then it would be 3, and quadruple would be 4. It's basically how much the population is growing by. Then we find k, the growth constant, which is every 6 hours. When you're doing these types of questions, you have to choose a time period that you want to use. I used hours. You can use days or minutes depending on what you're trying to show. But because I used hours and it's 6-hour time intervals, I had to put k as 1 over 6. Right beside the k value, I put the t, which is where we're going to sub in the number of hours that we're solving for. After that, once everything's plugged in, you just solve and find your answer. Part B is very similar, but the difference is that because we're working in hours, we're going to have to put it as 2 times 24 because there's 24 hours in a day and it's 2 days long. Then you just sub that into the exponent for t and then solve for the rest. A potential question could be when you're given the final amount but are asked to solve for another variable. In this example, you're given the final amount, which is 1,536 bacteria, but are asked to find the time. Here, all you have to do is sub the numbers into the equation and solve for the unknown variable using exponent laws. If you have information and are plotting an exponential growth function, they tend to look like this, where they're very curved and increase very fast and have an asymptote where they don't touch. And that's all for graphing exponential growth functions. I hope this review helped you and that you have good luck graphing your functions in the future.